In this final session on Laplace transforms, we are going to introduce Dirac delta functions. Actually, there is nothing much to learn from this section. Only thing which is required is you need to know what is the Laplace transform of the Dirac delta function. Only that much is required for your examination point of view. But still, I will try to introduce the basic concept for the introduction of this Dirac delta function. But that is not at all required for examination. Only you need to know what is the Laplace transform of this Dirac delta function. Okay, so basically Dirac delta function is actually used to model impulsive functions, okay, or impulsive forces. Okay, I hope you know what is an impulsive force from physics. It's basically a large force acting on a very short time period. It's a very large force acting on a very short time period. For example, cricket bat hitting a ball. Okay, so that is a very large force acting on the ball in a very short span of time. So such a force is called impulsive forces. Okay, for example, there are many examples of impulsive forces. For example, tennis ball being hit by a racket, a ship being hit by a single highway, an airplane making a hard landing, etc. These are some examples of impulsive forces. Okay, so often in applications, when you try to model applications, there may be impulsive forces. So when you try to form a differential equations out of the practical problem, you may have impulsive forces to be modeled. Okay, so when you try to solve those differential equations using Laplace transform, you will have to find the Laplace transform of those impulsive forces. So that is why we are introducing a new function called Dirac delta function to model those impulsive forces, so that the Laplace transform of such functions could be found very easily. Okay, so basically Dirac delta function is used to model impulsive forces. Okay, now let us try to define what's the Dirac delta function. Okay, so we cannot define Dirac delta function in a straightforward way, because it is a very complicated function, and moreover it is not a function at all. Okay, so as the name suggests, don't think that Dirac delta function is not a function in the mathematical sense. Okay, I'll explain it why. Basically, it's not a function because of some reasons. I'll also show you the reasons also, but it is not at all required for examination. Okay, so how to model an impulsive function using Dirac delta function? I'll define Dirac delta function later, but how to model an impulsive function? Okay, the basic property of an impulsive function is it's a very large force acting on a very short time period. Okay, so consider this problem, this figure. This figure actually represents a force 1 by k acting on an interval a to a plus k. If you look at this figure graph correctly, it actually denotes a force 1 by k, which is acting in an interval a to a plus k. Well, now what happens when your k is very small? When your k is very small, for example, if your k is maybe 0.05, that means your 1 by k would be 1 by 0.05, which will be a large quantity. Okay, so when k is small, your f is large. Okay, so basically these are very large forces acting on very short time period. Okay, so I am going to write a standard notation for this type of function. I am going to use the notation fk t minus a for this function. This t minus a from unit step function itself, you can understand this is actually used to relate and later convert this function in terms of step functions, but still this t minus a2 is used to show that this function is starting from the point t is equal to a. So basically this t minus a notation is used to indicate that this function is starting from the point t is equal to a, just like our unit step functions. Okay, and this k denotes this length of the interval k. Okay, now this is defined as 1 by k when your t varies from a to t a plus k, and elsewhere it is simply 0. So this is your some special functions which are used to model impulsive functions. Okay, now when this k tends to 0, what will happen? Your f will go on to increasing until it becomes infinity. So when k tends to 0, you will be getting this limiting function as infinity, where t is equal to this a, because k is going to 0 and 0 elsewhere. Okay, so when k tends to 0, this function would be going to the limit infinity when t is equal to a and 0 elsewhere. So this limiting function is called the Dirac delta function, which is denoted by the symbol delta t minus a. Okay, so delta t minus a is defined as infinity when t is equal to a and 0 elsewhere. Or in other words, what is delta t minus 2? Delta t minus 2 is simply infinity when t is equal to 2 and 0 elsewhere. Okay, I hope it is clear what do you mean by the Dirac delta function. Okay, so before we discuss the properties of Dirac delta functions, please kindly make use of this observation. So you can see that what will be the area of from 0 to infinity fk of t minus? What is this area? What is the value of this quantity? So if you know that the area is actually the area of the graph. So the integral 0 to infinity fk of t minus a is actually the area under the graph. So what is the area under the graph? It is a rectangle. So the area will be simply length into breadth, which is 1 by k into k, which is nothing but 1 here. So the length of this rectangle is actually 1. So it is 1 here. Okay, so area of integral 0 to infinity fk of t minus a dt is simply 1. Okay, now since the Dirac delta function is a limiting case of this fk t minus a, it can be considered as integral 0 to infinity delta t minus a is also 1, because each of the component functions has the integral 1. This can also be considered as the area integral 0 to infinity delta t minus a dt is considered as 1. Okay, now this is why precisely the reason why this delta cannot be considered as a function. Okay, because if you look at the definition of delta, it is not required for you. I'm just emphasizing once more, this is not required for you, but I'm just telling it for the sake of completeness. You can see that this delta is actually defined only for a single point, but still the integral of that function has a finite value. Okay, for example, if your function is f of x is equal to 1 and 0 elsewhere, when you integrate, definitely the value will be 0. Okay, so when your function is just defined at a single point, okay, so and when you integrate that, the area under that figure, what will be the, so when you draw that figure function, what will you be getting? The function is basically the value is only 1 only. So what is the area under this graph? Nothing is there, so your area should be 0. Okay, so in that similarly, so for a normal function, if it is defined only at a point, and if everywhere else it is 0, its integral value should be 0. But for this Dirac delta function, you are getting the integral value is 1. So this is not a usual function, so it cannot be considered as a mathematical function because of this reason. Okay, but still for application's sake, if you can just assume that this is a function, okay, just assume it is a function, many difficult problems can be solved very easily. That is why they are considering this as a function for application sake. So because in order to make some applications easier, we are just assuming that this is a function. Okay, and usually this integral value, it's an area, it's the area under the graph. It is also called the impulse of the function. Okay, so the impulse of the function in mechanics is defined as simply integral over the time period where the function is acting fk of t minus a dt. That is the definition of impulse. This is not required for you. You just need to know what is the definition of impulsive force and just need to try to understand what is it. That only is required for you. None of these concepts are required for an examination point of view. All this was talked just for the sake of completeness. It is not required for you. But try to understand the definition of Dirac delta function and also have the idea that it is actually not a function in the usual sense because of this problem. But this is just for your conceptual clarity. Okay, so now let us try to understand what is the Laplace transform of this Dirac delta function. We are going to find the Laplace transform of this Dirac delta function. Okay, so before that, this is the functions which we have discussed earlier, and similarly the area also we have discussed, the Dirac delta function also we have discussed. Okay, so this property also we have discussed, and this is why it is not considered as a function in the usual sense. Okay, now let us try to find the Laplace transform of the Dirac delta function. Okay, now the definition of the Dirac delta function is delta of t minus a is actually infinity when t is equal to a and 0 elsewhere. Now using this definition, you cannot find the Laplace transform directly because your integral will have integral 0 to infinity. So infinity will be coming inside the integral, so you cannot use the definition directly. So what I am going to do is that I am going to find the Laplace transform of delta t minus a as the limit of the Laplace transforms of the other limiting functions. For example, limit of Laplace transform of limit k tends to 0, the Laplace transform of fk t minus a. So I am going to find the limit of the Dirac delta function as the Laplace transform of the limit of these functions. Okay, the derivation is not required for you, but for the sake of combination, I am just derive it for you also. So what is fk t minus a? Fk t minus a is defined as simply 1 by k, where a less than t less than a plus k and 0 elsewhere. Okay, now I need to find the derivative of find the Laplace transform of this. Now this is a function which is defined only for a particular interval, so you can use the step function property there. So it is simply limit k tends to 0 Laplace transform of fk t minus a. I am going to write using step function, so it will be 1 by k into u of t minus a minus 1 by k into u of t minus a plus k. Okay, so 1 by k into u of t minus a into 1 by k into u of t minus a plus k. Okay, now what is it? So it is actually limit k tends to 0. Okay, L into 1 by so 1 by k in 1 by ks into e raised to minus as. This is by the second shifting theorem, where you know that the Laplace transform of f of t minus a into u of t minus a is simply e raised to minus as into f of s. So this is, I have written this from second shifting theorem, plus minus again 1 by ks into e raised to minus a plus k into s. So limit k, so this is the value, limit k tends to 0 of this. Okay, if you want, I can simplify it further. So here the limiting value is k, so keep k as such. So rest everything you can take it outside. So this is, you can write this as e raised to minus as by s into 1 minus, if you write it correctly, e raised to minus k. So basically limit k tends to 0, 1 minus e raised to minus ks. Okay, minus as I have taken out outside by k. Okay, so I have to find the value of this quantity. It's very simple. Derivation is not required for you, but it's very simple. If you want, you can try that also. Okay, now this is actually by 0 form, because when you put k is equal to 0, you will be getting 0 by 0 form. So we can apply the L'Hopital's rule or L'Hospital's rules here. So it will become e raised to minus as by s into, so when you take the derivative of numerator by denominator, so it's actually limit k tends to 0, derivative of e raised to minus k is actually k into e raised to minus ks by 1. So here k into, so it is actually k into e raised to, no, it's not k, because you are actually differentiating with respect to s only, because k is the variable here. So it will be simply s into e raised to minus ks by k, because the variable here is actually k. So when you put k is equal to 0, what will you get? This will be so by 1 here, because of the derivative of numerator by derivative of denominator. So when k becomes 0, you will be just getting the values s, or it is e raised to minus s. So the Laplace transform of Dirac delta function is simply e raised to minus as. Okay, so for examination per point of view, only this much is required from this discussion, nothing else is required. So remember, the Laplace transform of delta t minus a is simply e raised to minus a. Only this much is required for you, nothing more is required. So just read this. Even if you have not understood the previous things, there is no need to study that. Only this much is required. Okay, now let us try to solve problems containing this Dirac delta function. Okay, nothing new is there. We can use all the earlier properties plus this new property of Laplace transform. Only that much is there. Okay, for examples, you will be given problems like this. Okay, nothing more is there from the section. You will just be given problems like this. For example, your problem would contain this delta. Okay, or in some problems they can also give the u also. Okay, so it's just that. So suppose you are getting given a problem like this, you have to solve this problem. What will you do? What will you do? Just take the differential equation, take the Laplace transform and apply the transforms, find the value of L of f of t, and then apply the inverse transform. That is what is required. For example, if I am doing this problem, what will I get? I will take the equation which is y double dash plus 2y dash plus 2y is equal to delta t minus 3. I will apply the Laplace transform, so it will become L of y double dash plus 2 of L of y dash plus 2 of L of y is equal to L of delta t minus 3. You know this, what is this? It is simply e raised to minus as, so it is raised to minus 3s. So this is the only utility of Dirac delta function. Okay, now the utility of Dirac delta function is over, we will not use it again. So just for finding the transform of Dirac delta function is this section introduced for you. Okay, nothing more is required, only this much is required for you from the examination point of view. Just you need to know how to find the transform, only that much is required. Okay, now we can do the problem in the usual form. So what is the value here? So it is s square into L of y minus s into y of 0 minus y dash of 0 by differentiation formula plus 2 into s into L of y minus y of 0. Okay, again plus 2 into L of y is equal to e raised to minus 3s. Now y of 0 is 0 and y dash of 0 is again 0. So this will become 0. This is 0. So the value is actually s square plus 2s plus 2 into L of y is equal to e raised to minus 3s, or your L of y is e raised to minus 3s by s square plus 2s plus 2. Okay, now you have to find the inverse transform. Okay, so that is also very easy for you if you understand this. This is of the form of the second shifting theorem, e raised to minus as only. So first I will find the inverse transform of 1 by s square plus 2s plus 2. What is it? So you can apply the many methods here, but I'll apply maybe the first shifting theorem. So I'll rewrite the denominator as 1 by s plus 1 the whole square plus 1. This is by the completing a square method which you have studied in the first shifting theorem. So this is actually of the form 1 by s square plus 1. So the inverse transform would be 1 by s square plus 1 is basically sine t. Now it has s plus 1 in place of s, so it is the factor of e raised to minus t is also there. So the inverse transform of 1 by s square plus 2s plus 2 is simply sine t into e raised to minus t. So this is the inverse transform of this would be, this is your f of t. So the inverse transform of this is actually f of t minus a into u of t minus a by the second shifting theorem. Your a is 3 here, so the value here is sine t minus 3 e raised to minus t minus 3 into u of t minus 3. Okay, so this is the value of y of t. Okay, so there is nothing from this section which have been used. All these concepts we have discussed in the previous classes, including differentiation formula, completing a square, first shifting theorem, and then step function, and then their second shifting theorem. Okay, so all these concepts have been discussed in the previous videos, so go through those videos to understand these steps. Nothing new is there. Only thing we have discussed is basically the transform of delta t minus 3. Nothing more is there. Okay, so this is Dirac delta function. So you need to know only the Laplace transform of Dirac delta function to do problems from this section. Okay, some practice problems are given to you. Okay, you can also try those problems here. Okay, so you can see that in those problems delta is coming. So the only utility of that is you should know what is the Laplace transform of this quantity. So when you take Laplace transform here, it will be simply be 4 into e raised to minus 3 pi s. Okay, so for that they are giving this thing. Okay, so that's all. So that's the end of this module. Okay, so we'll start with Fourier transforms in the next module. Okay, thank you.